In this video, we're going to begin to discuss path independence of line integrals of vector fields. To get started, we'll start with the definition of path independence. So we'll say that this line integral over curve C of the vector field F is path independent if I take this line integral over two different paths, let's say C1 and C2, and these two integrals are equal, and this is true for any two paths, C1, C2, with the same initial point and terminal points. So in other words, if a line integral is path independent, then we don't care about the curve itself, we just care about where the curve starts and where the curve ends. And so if we somehow know that an integral is path independent and we want to compute this line integral over a complicated curve, we could actually use the path independence to say, well, we don't have to integrate over that curve. We could actually just find the straight line segment between the 2 points and integrate over that. And so path independence is a really powerful property that some line integrals have that allow us to switch the path to a simpler one without changing the value of the integral. It would be nice if all line integrals had this property, but unfortunately, that's not the case. So not all line integrals are path independent. Right, so if we want to be able to use this property, we will have to determine ways to analyze a line integral and determine if it's path independent before we can start changing the paths. We've actually seen an example of a non-path independent line integral already, so let's recall that. So in one of the previous videos, we considered the line integral of y squared dx plus x dy, and I computed an example over a curve C1, which was the line segment from the point negative 5, 3 to the point 0, 2. And I don't remember the value off the top of my head, but we did compute this in one of the previous videos. And then I asked you to compute the line integral of the same function over the curve C2, which was the arc on the parabola y equals 4 minus x squared from t equals negative 3 to t equals 2. And when you did this, what you would notice is that when t is equal to 3, or I'm sorry, when t is equal to negative 3, you're actually at the point negative 5, 3. And when t is at the value of 2, you're actually at the point 0, 2. So C1 and C2 are both paths from the point negative 5, 3 to the point 0, 2. They just take a different route to get there. The C1 is a direct line segment from one point to the other, and C2 takes a parabolic arc to it. And so we saw that these two line integrals had different values. Right? Now you might say, well, this is not a line integral of a vector field, as I just defined path independence for. However, recall that we also have an alternative way of writing vector field or integrals of a vector field. And so in this case, this is the same thing as the line integral over C of the vector field F, where F is defined as the functions y squared and x. All right, we justified this at the end of the videos on line integrals, that the line integral of f dr can be written in this form, the line integral of p dx plus q dy. All right, so in this case, we do have a line integral over a vector field. And if in case it's bothering anyone, this first integral I wrote should have a c there to indicate that it's over the curve. But we do have this vector field C, and we've seen here we have two paths, C1 and C2, that give us different values. When we integrate these, we've already done this. And so this integral above is not path independent. Okay, so here's an example of one, and a relatively simple one. The component functions are y squared and x, very simple functions. So this is a non-path independent line integral. Right, that leads us to the question of, if we have a line integral, how do we actually determine if it is path independent or not? We sort of have to know that before we go to compute it in order to know if we can make a simpler path or not. And so in order to get a result that states an answer to that question, let's quickly recall a definition. So we say a vector field F is conservative if that vector field is the gradient vector field for some function f. All right, we know the vector field of, or the gradient vector of a function is always a vector field, and so this is one property that a general vector field can have, is whether or not it is the gradient of some function. And if it is, that function f is called the potential function. Okay. And it turns out that this is one of the useful properties that allow us to determine path independence. Okay. So we have a really important result called the fundamental theorem of line integrals. And as you imagine, you know what the fundamental theorem of calculus says, and this is going to say something very, very similar, hence the similar name. Right? And so to get this all set up, what we need is we need to let C be a smooth curve. Given by a vector function r of t, and t ranging from a to b. Right? Notice that this curve can be a curve in the plane, in which case r is a vector function with 2 components, or C could be a curve in 3 space, and r is a vector function with 3 components. Right? I also want to let f be a differentiable function of either 2 or 3 variables, with the gradient of f being continuous. Continuous specifically on C, so continuous on those points. It could be discontinuous at other points, but it needs to be continuous at every point on the curve C. And if we have this general setup, then the line integral over C of the gradient of f dr. Notice this is the line integral of a vector field. It's the line integral of a conservative vector field. This is equal to f of r of b minus f of r of a. Right? And so this looks exactly like the fundamental theorem of calculus to some degree. We have the integral of the gradient vector of f. The gradient vector is just the partial derivatives in a vector form. And so in normal fundamental theorem of calculus, you take your integrand function and you find an antiderivative. So if you have the integral of a derivative, you're going to find the original function, and you're going to evaluate it at the endpoints. And in the context of line integrals, this is exactly what we're doing. F would be the sort of antiderivative function. It's the function who gives you the gradient vector field that you're integrating on. And they're evaluating it at r of a and r of b. Those are the endpoints of the curve that we're integrating on. And then we're substituting the endpoints into the function and we're subtracting. And so you can hopefully see why this is called the fundamental theorem of line integrals. It just mimics the fundamental theorem of calculus in the analogous way. And also, if we break this down a little bit, we notice that this is the gradient of f, so this applies to any conservative vector field. Because those are exactly the ones that we can write in this form. And these are the endpoints of the curve, the r of b and r of 0. And so what this theorem really tells us is that if I have the line integral of a conservative vector field, all I need to know are the endpoints of the curve C. I don't need to know the actual curve, and I don't care about what happens in between. I just need to know where it starts and where it ends. And so the punchline here is that line integrals of conservative vector fields are path independent. And so if we know our vector field is conservative, then finding the line integral over any curve is really just amounts to knowing where the curve starts and where the curve ends, and being able to evaluate the function f, the potential function, at that those particular points. Now, it might seem like coming up with this particular theorem and verifying it would be difficult, but it is actually rather straightforward and combines a few of the things that we've talked about previous in the course. So let's take a minute and just look at why this particular fundamental theorem holds. Right, so we want to compute the line integral over C of a conservative vector field, which we can write as the gradient of f. Now we know, given all the information that we had about the curve, that we can rewrite this as the integral from a to b of the gradient of f evaluated at r of t dot product with r prime of t dt. This is just our definition of the line integral of the vector field. Right? We can write out what each of these vectors are. So the gradient of f we know is del f del x, del f del y. And I'll do it in 3 dimensions, although if it were only in 2 dimensions, you would just ignore this third component. And then r prime of t is going to be dx dt, dy dt, and dz dt. And again, if we're in 2 dimensions, we just leave out the third component of each of these vectors. Okay. Well, we know how to take a dot product. So this is going to be del f del x times dx dt plus del f del y times dy dt plus del f del z dz dt And if we look at that expression in square brackets, that should look familiar to us. That is a version of the chain rule for partial derivatives. And so that is simply the derivative with respect to t of the function f of r of t. Right? And so this here, going from this line to this one, this is the chain rule. Okay. And now what are we doing? We have a function simply of one variable t, and we're integrating it from a to b dt. And so this is just a standard integral. And so what I need is to find an antiderivative of this function. Well, that's very easy in this case. The function is a derivative of some function, so we can just take that function itself as our antiderivative. So f of r of t evaluated from a to b. And when we do that, we get f of r of a minus f of r of b minus f of r of a, which is exactly what the fundamental theorem of line integrals stated we would have. And so the underlying principle here in that fundamental theorem is the chain rule for partial derivatives. And that's maybe a little surprising if you haven't seen this kind of thing before. Okay, let's look at an example where the fundamental theorem of line integrals is useful in evaluating a line integral. Let's suppose we wanted to evaluate the integral over curve C of y dx plus x dy over the following curve. So the curve C is going to be the arc of the circle centered at the origin, with radius 5. From the point 5, 0 to the point 3, 4. Right, now the first thing to remember is that this is a line integral of a vector field. In fact, it is the line integral over the same curve C of this vector field f, where f is the vector field y, x. Right, these are the component functions of the scalar fields for our vector field. So we're integrating this vector field y comma x. So if we want to use the fundamental theorem of line integrals, we do need to know that this is conservative. We need to know this is the gradient vector field for some function f. So our first step is we need to find the potential function f, if such a potential function exists. And we will come back in a little bit and look at how to do this in general, but this function is relatively easy. We want a function that if I differentiate with respect to x, I get y. Right? So we want the derivative of f with respect to x to be y, and the partial with respect to y to equal x. And so in this case, it's not hard to see that our function f can be the function xy. All right, we can also throw on a constant if we like, but the function xy will work for this particular one. Now, like I said, we will come back to a more methodical way of finding potential functions shortly, but for now, this is good enough for this example. Right? And so, given that we have this, the fundamental theorem of line integrals tells us that the integral that we want, the line integral over y dx plus x dy, is simply f of 3 of 4, the potential function evaluated at the second endpoint of the curve, minus f of 5, 0, the potential function evaluated at the beginning of the curve. Right, and the function just multiplies these numbers together. So we have 12 minus 0, which is 12. So the value of this integral, using the fundamental theorem of line integrals, and ignoring the fact that that we have the curve being an arc of a circle, we can simply compute the endpoints, the function at the endpoints, and subtract to get 12. Right. Now, we could, of course, do this using just the definition of the line integral by parameterizing this curve C and going through that process. And if you really want to, I'd encourage you to do that. However, if we did do that, the vector function, the easiest vector function to parameterize the circle at the origin of radius 5, would be given by 5 cosine t, 5 sine t. And this is not a terrible function to have to deal with. However, when we look at the range for t, the values for t, t is going to start at 0. But then the upper endpoint, to get to the point 3/4, we would have to consider the inverse tangent of 4/3. And so you're going to have to compute an integral from 0 to the inverse tangent of 4/3. And when you take the dot product, we're going to get cosine squared and sine squared. So you're going to have to, among other things, bring in the half angle identities in some way. And you'll end up getting 12 eventually. But it is a very nasty calculation. It is certainly more difficult than what we just did above, where we subtracted 12 and 0. And so this is really where the fundamental theorem of line integrals, where it becomes helpful, is to be able to compute things like this when we know we have a conservative vector field, and we have the potential function, or can easily obtain the potential function, and we can quickly compute a value of a line integral.